Welcome to the deep dive. We're really thrilled to have you with us today because we are looking at a stack of research that is fundamentally rewriting our understanding of reality.
Yeah, it really is.
Imagine for a second the current state of theoretical physics. It's the year 2026, and the field is undergoing this massive revolution, but it is absolutely not the kind of clean, mathematically perfect revolution that people predicted a few decades ago.
No, not at all.
It's a ruthless, gritty reality check. For years, the quest for an elegant theory of quantum gravity was the holy grail of science. Now, the tone has entirely shifted. We have a massive stack of sources to go through today, primarily anchored by a comprehensive 2026 academic dossier titled The Architecture of Quantum Gravity, along with a really fascinating stack of supporting research papers.
And they are dense.
Very dense. So our mission for this deep dive is to cut through all that incredibly heavy math and map out exactly how the rules of the universe are being rewritten. We're going to take you from the so-called swampland of string theory all the way to the radical emerging consensus that the universe might just be a giant information processor. So, okay, let's unpack this.
We really are at a fascinating inflection point in physics right now. And the reason you should care about this shift is that we are no longer just asking what the universe is made of. We are asking how it computes reality.
Right.
For the longest time, the physics community was searching for the perfect equation, the single mathematical string that would gracefully tie gravity and quantum mechanics together. But as this 2026 dossier clearly lays out, that search has hit a wall of immense complexity.
A massive wall.
Exactly. The answers researchers are finding now are shattering old assumptions and forcing us to look at the universe not as a collection of physical objects, but as a dynamic web of information.
That is exactly where this concept of the swampland comes into play, which I have to say is such a great term for a physics concept.
It really is descriptive.
In string theory, researchers used to just look for mathematical perfection. If the math worked out on a chalkboard, they assumed it could describe a possible universe. But in 2026, physicists are taking a totally different approach. They are actively mapping out physical impossibilities.
Yeah, the constraints.
Right. I was reading through the dossier, and the best way I can picture it is like an old explorer's map. You have this tiny, stable island called the landscape, which represents the consistent theories of quantum gravity.
For ones that actually work.
Exactly. But surrounding that island is the swampland. This is a massive, endless ocean of theories that might look totally fine on the surface. They don't have obvious mathematical errors, but the second you apply the actual rigorous rules of quantum gravity, they fundamentally break down. They're essentially mirages.
That is a perfect analogy. What's fascinating here is how this swampland program has evolved from a niche theoretical idea into the dominant framework for testing models right now. And the major breakthrough around 2025 and 2026 has been connecting this swampland map to holography.
Oh, holography.
Yeah. Now, in physics, the holographic principle suggests that all the information contained in a 3D volume of space can be thought of as encoded on a 2D boundary surrounding that region.
Right, like a security hologram on a credit card containing a 3D image on a flat surface.
Precisely. Researchers looked at the strict mathematical consistency conditions on that 2D boundary. They were looking at complex rules, things like the modular bootstrap, which are essentially mathematical safeguards that ensure the 2D boundary equations don't contradict themselves.
Okay.
What they proved is that those exact same mathematical rules on the boundary map directly to the physical boundaries of the swampland in the 3D space inside. It is essentially mathematical proof that the geometry of quantum gravity is just a manifestation of deeper underlying informational rules. The traditional boundary between physical space-time and pure quantum information is completely dissolving.
Which creates some incredibly dramatic tension for cosmologists, especially when the dossier gets into the de Sitter swampland conjecture.
Oh, absolutely.
As I understand it, this conjecture basically argues that stable de Sitter vacua cannot exist in quantum gravity. But help me out here, because in plain English, a de Sitter vacuum describes a stable universe that is accelerating outward.
That's right.
And isn't that exactly what our universe appears to be doing right now? It seems like a massive conflict. If this conjecture is true, our whole understanding of the cosmological constant, the idea that dark energy is just a static, unchanging force pushing the universe apart, has to be entirely wrong.
You've hit on the exact reason this is causing such an uproar. If the swampland conjecture is right, a static cosmological constant is impossible. And this is not just abstract chalkboard math anymore.
Right, we can test it. It's exactly. In 2026, this theoretical tension is driving major observational studies. Researchers are heavily relying on the DSI data, that's the Dark Energy Spectroscopic Instrument. They're combining that telescope data with advanced machine learning and genetic algorithms to test if dark energy is actually dynamic.
So they are looking to see if dark energy changes its strength over time.
Exactly. They're testing a concept called quintessence. Instead of a static cosmological constant, quintessence suggests dark energy is an evolving, fluctuating field. If the swampland limits of string theory are correct, dark energy absolutely has to be changing over time.
It's wild to think that the mathematical limits of string theory, something we can't even see, are dictating how we observe the actual night sky and measure galaxies.
It really connects the micro and the macro.
And the dossier doesn't stop there with the swampland. It also highlights the weak gravity conjecture. This rule essentially says that gravity absolutely must be the weakest fundamental force. But why is that so important? The paper mentions it has something to do with black holes decaying. Yeah, if we connect this to the bigger picture, it is about preserving the laws of thermodynamics. If gravity weren't the weakest force, charged black holes wouldn't be able to decay completely.
It just gets stuck.
Exactly. You would end up with these infinitely stable microscopic remnants left over, and those remnants would hold an infinite amount of quantum states, which completely breaks the laws of thermodynamics. Recently, in 2026, there have been massive thermodynamic studies on a specific type of black hole called Euler-Heisenberg black holes.
What makes those black holes so special?
They incorporate quantum electrodynamics, basically, how light and matter interact at the quantum level in incredibly strong magnetic fields. By studying these specific black holes, researchers established a universal relationship between entropy and extreme mass-to-charge ratios.
So it proves the concept.
It essentially provides hard thermodynamic proof for the weak gravity conjecture. This stabilizes the whole concept of cosmic censorship, the idea that the universe always hides its singularities behind event horizons. It proves that these black holes will eventually decay, which keeps the entire swampland framework incredibly stable.
Okay, so that is the top-down approach, trying to whittle down string theory from the macro level by figuring out what is mathematically impossible. But the dossier takes us in a completely different direction next, a bottom-up approach. Specifically, we are looking at loop quantum gravity, or LQG, and emergent gravity.
A completely different philosophy.
Right. Now, loop quantum gravity has always been the rebel alternative to string theory. It doesn't assume a background spacetime exists at all. It tries to build space from scratch. I was reading this section, and they mention a massive breakthrough where researchers have successfully modeled spin networks as regular tetrahedral lattices. But the math got pretty heavy. What exactly did they figure out here?
It's a stunning achievement. By applying methods from solid-state physics, the same physics we use to understand crystals and metals, to quantum geometry, they have given us a concrete, discrete model of space. They actually calculated the specific spacing between the nodes in this lattice of spacetime.
And they got an exact number.
They did. It comes out to exactly 2.707 Planck lengths. And they are describing the dynamics of these nodes using a Hamiltonian operator that integrates the Lennard-Jones potential, zero-point energy, and harmonic oscillations.
Wait, a Lennard-Jones potential, isn't that what chemists use to describe how molecules stick together and repel each other?
Exactly. They are treating the fundamental fabric of space like a physical material.
I love the visual this creates. Imagine flat spacetime not as a smooth rubber sheet, which is how Einstein pictured it, but as a graviton-rich lattice. And the movement of gravitons through this space is literally modeled like Brownian motion. It's a stochastic random walk.
It's a very visceral way to think about it.
Gravity isn't a smooth, continuous field anymore in this model. It is statistical mechanics. It is like looking at a glass of water. From far away, it looks perfectly smooth, but zoom in, and it's a chaotic mess of bouncing molecules. That is what loop quantum gravity says space itself is doing.
That analogy perfectly sets up the next major concept in the dossier, emergent gravity. This was pioneered by Eric Ferland, and it argues that gravity isn't a fundamental force of nature at all.
Which is such a crazy thought.
It is, but the math is compelling. Instead of a force, it is a thermodynamic side effect. It's the result of the universe trying to maximize its entropy. Just like heat naturally flows from a hot object to a cold one, objects fall toward each other because it is the most statistically probable way for the universe to organize its fundamental information.
The dossier mentions a huge correction to Verlin's work in 2026. For years, his equations were close, but not quite matching observations of the universe perfectly. What exactly did they fix?
Researchers realized there was a missing two-thirds factor in his original calculations regarding the volume entropy of the universe.
Just a missing fraction.
Yeah, just a fraction. But when they applied this fix, the critical value in the math known as the Milgram constant shifted. It became exactly the speed of light times the Hubble constant, divided by 9.
Wait, so by just fixing a mathematical fraction, his whole theory of gravity as an illusion suddenly works?
It doesn't just work. The proof is absolutely stunning. They took this newly corrected emergent gravity model and tested it against the observed radial accelerations of 23 dwarf spheroidal galaxies.
And those are notoriously hard to model, right?
Exactly. These are incredibly faint, low-mass environments where classic Newtonian physics and even our standard dark matter models really struggle to make accurate predictions. The corrected emergent gravity model predicted the observations better than classic dark matter models in 21 out of those 23 cases.
21 out of 23. That is an incredible hit rate for a theory that says gravity is basically just an illusion of entropy. It is such an aha moment. You realize that maybe we haven't found dark matter particles yet because they literally don't exist. Maybe the space itself is just acting differently at those incredibly weak acceleration scales because of how the universe handles information.
It is a profound shift in thinking, and it naturally leads us into what is perhaps the most radical framework in the entire 2026 dossier, the Information Universe and the Primordial Quantum Field, or PQF.
This part really blew my mind.
It takes the idea of emergent gravity and pushes it to the absolute limit. It argues that space, time, and matter do not fundamentally exist at all. They are entirely secondary phenomena. Everything emerges from a continuous, non-local informational substrate.
Hold on. If space and matter don't exist, what are we sitting in right now?
According to the PQF model, you are sitting in a complex data structure. The model rejects the idea of quantizing space-time entirely. Instead, the universe is governed by an equation driven by complexity entropy.
How is that different from regular entropy?
Good question. Normal entropy just measures disorder or chaos. Complexity entropy measures the degree of structural organization and long-range correlations in this underlying informational field.
So if I'm tracking the Big Bang, it wasn't an explosion of matter and heat like we've always been taught.
In this model, the Big Bang was an informational phase transition. It was the moment the universe crystallized from a state of total incoherence into a highly organized informational structure. Just like water freezing into ice, the universe snapped into a structured state of data.
This is completely mind-bending, but how do you prove something that abstract? We can't just stick a thermometer into the informational substrate.
That's the brilliant part. The PQF model actually makes testable predictions. One of them is the existence of entanglement waves.
Like gravitational waves.
Similar concept, but entirely different mechanism. These are not your standard gravitational waves that warp space and time, like the ones from colliding black holes. These are literal fluctuations in the entanglement density of the universe's informational substrate.
And the paper suggests we might be able to detect these entanglement waves using incredibly sensitive Bose-Einstein condensates right here on Earth. It is amazing that we can test the fundamental code of reality in a lab. But here's where it gets really interesting. Because whether you are dealing with the swampland of string theory or the emergent lattices of loop quantum gravity, the math has become too complex for human brains to handle alone.
Far too complex.
We're talking about 10 to the power of 500 possible vacuum states in the string landscape. You could have every human on Earth doing math for 1 billion years and you wouldn't even scratch the surface. So how are they actually making progress in 2026?
That is where they had to call in the cavalry. Specifically, artificial intelligence. The integration of AI into theoretical physics by 2026 is nothing short of a rescue mission for string theory.
A rescue mission.
Truly. Traditional analytical research had essentially hit a brick wall. But today, the use of AI to navigate this hyperdimensional space is the absolute standard. For example, researchers are using convolutional neural networks, which is the exact same kind of architecture used for facial recognition on your phone to predict the topological invariance of Calabi-Yau manifolds.
And just to clarify for everyone, Calabi-Yau manifolds are those tiny, curled-up extra dimensions that string theory requires to make its equations work, right?
Exactly. The math to calculate their properties, specifically their Hodge numbers, which define their shape, used to take days of computing time on a supercomputer for just one complex shape.
Now.
The trained neural networks in 2026 are doing it in milliseconds, with over 95% accuracy.
That is a staggering leap in efficiency.
Furthermore, they are using unsupervised learning algorithms to explore the landscape without any human bias. And they're finding typical regions. They're identifying massive clusters of universes in the math that share similar physical parameters, like mass hierarchies and coupling constants.
So they're narrowing the search.
Significantly. This is vastly accelerating the search for the specific mathematical corner that perfectly describes our standard model of particle physics. AI isn't just crunching numbers. It is recognizing patterns in the fundamental code of reality that human minds simply couldn't see.
Okay, so we have all these beautiful, terrifyingly complex theories. But as you're listening to this, you might be wondering, how do we actually prove any of this with physical evidence? Is this all just incredibly sophisticated math, or is it physics? The dossier details two massive observational windows opening up right now in 2026 that could provide the hard data we need. What's the first one we're looking at?
The first major test comes from LISA, the Laser Interferometer Space Antenna. LISA is currently preparing to detect the stochastic gravitational wave background, but specifically, it is hunting for the background noise generated by evaporating primordial black holes.
The microscopic ones.
Yes, these are microscopic black holes that formed in the very first fractions of a second of the universe. Because gravitons escape from these evaporating black holes without scattering, they preserve a direct spectral record of the event. Any deviation from Stephen Hawking's original predictions regarding how these black holes evaporate will give us a direct, undeniable read on string theory effects or loop quantum gravity corrections at the Planck scale.
It's like listening to the echoes of the Big Bang to hear if the universe is made of strings or loops. And the second massive observational window involves the cosmic microwave background, the CMB. Recently, analysis of the Planck legacy data confirmed a very specific anomaly, a 0.30 plus or minus 0.05 degree rotation in the polarization of CMB photons as they travel across the universe.
That's right.
This is called cosmic birefringence. It sounds super technical, but it's a massive clue. It points heavily toward parity-violating physics.
To put parity-violating physics into perspective, imagine flipping a mirror image of the universe. Parity violation means that mirror universe wouldn't actually function the exact same way ours does.
It wouldn't be perfectly symmetrical.
Exactly. It means the universe has a fundamental, built-in preference for left-handed or right-handed interactions, which is a key feature in many string theory models. Finding this rotation in the CMB is a huge piece of the puzzle.
These observational tests are crucial right now because as we dive into the final section of the dossier, they highlight a profound sociological shift in the physics community. There is a full-blown theory crisis happening in 2026. Because string theory has dominated theoretical physics for decades without providing direct experimental confirmation, we are seeing a deep divide in the academic world, and we have to report on this controversy exactly as it stands because it is literally tearing university departments apart.
It is a very heated landscape. On one side of the divide, you have fierce critics. The source material explicitly names physicists like Peter Woit and Sabine Hossenfelder. In the ongoing academic debate, critics of this nature are sometimes labeled by their opponents as methodological terrorists, which gives you an idea of how intense the rhetoric has gotten.
It sounds like physicists are getting into the academic equivalent of street brawls on social media over multidimensional geometry.
They absolutely are. The core argument from the critics is that string theory has become not even wrong. Because it has 10 to the power of 500 possible solutions, they argue it lacks any falsifiable predictions, and that the field has just lost itself in increasingly complex, untestable mathematical structures. They believe physics has detached from reality.
But on the other side of the divide, you have major academic centers and pop science media platforms you know well who continue to champion string theory as the ultimate and perhaps only mathematically viable theory of everything. The proponents argue that the math is simply too deep, too elegant, and too interconnected to be a coincidence. They argue that the experimental technology simply hasn't caught up to the theory yet. It's vital to note that we are not taking a side here. We are just outlining the current state of this academic civil war.
And if you want to see how this debate is actually going to be resolved, you have to follow the money. And the money is moving rapidly. In 2026, massive funding bodies like the National Science Foundation and the Department of Energy are heavily pivoting their budgets.
Away from pure theory.
Yes, they are directing funds away from pure, abstract string theory research and pouring it into experimental synergies. They are funding the integration of AI into high-energy physics and prioritizing multi-messenger astronomy. The mandate from the people holding the checkbooks is clear. Theorists must provide observable, testable results.
Produce results or lose funding.
Exactly. The Simons Foundation, for example, is funding massive workshops that literally force computer scientists and string theorists into the same room. The goal is no longer just mathematical beauty, it is computational viability and observable reality.
So what does this all mean? We have covered the swampland mapping out physical impossibilities, Luke quantum gravity turning space-time into a bouncing lattice, emergent gravity predicting galaxy rotations without dark matter, and the universe as a primordial quantum field computed by AI.
If there's a single core takeaway for you as a listener, it's this: the universe is fundamentally an information processor. The era of elegant guesswork, where physicists hoped a single simple equation would explain everything, is definitively over.
It's a new era.
Completely. Whether reality is ultimately made of vibrating strings, discrete loops, or complex data gradients, the physics of 2026 is entirely about rigorous, data-driven consistency. The artificial boundaries between gravity, quantum mechanics, and information theory have collapsed. Space-time is not a stage where things happen. It is an emergent fabric woven by the entanglement of quantum data.
It is a totally new paradigm. But before we go, I want to leave you with one final, deeply provocative thought from the source dossier that we haven't even touched on yet. As if all of this wasn't mind-bending enough, researchers are also exploring something called the omega point theory.
That one is really out there.
It really is. This is a highly speculative model that suggests particles and fields aren't the fundamental building blocks of the universe at all. Instead, the universe is made of agents units that have innate informational processing capacity.
Yes, in this framework, the entire evolution of the universe is just a journey from a state of total incoherence, which they call the alpha point, toward a state of omniscient ultimate complexity, the omega point.
And the gravity aspect is wild, too.
Right. It even divides gravity into two types. You have alpha gravity, which is the force that pulls things toward simplicity, and omega gravity, which is a fundamental drive toward complexity. It suggests the universe is literally evolving to know itself.
And if that doesn't keep you awake tonight, consider the small patch hypothesis. This model suggests that the reason our observable universe looks so uniform and flat isn't because of cosmic inflation, like we've always thought. Instead, it argues that our entire observable universe, everything we can see with our most powerful telescopes, is just a tiny, low-entropy bubble floating in a massive, fractal, highly disordered background. We might just be living in a rare, quiet neighborhood of an infinitely chaotic multiverse. I invite you to mull over those incredible ideas. We want to thank you for joining us on this deep dive into the architecture of reality. Until next time.